again to thank Professor Wang for his very useful and nice presentation. Thank you very much, and hope to see you again face to face, maybe here or in China or in other places in the world. Thank you very much.
Yeah.
Okay.
Yeah, okay. Thank you. Yeah. Okay.
Yeah. Thank you very much.
Yeah.
The next presentation is about control of optical resolution beyond the diffraction limit in curved space. The speaker is Professor Jingxuan Zhang. Professor Zhang, are you here?
Yeah, I'm here. Can you hear me?
Nice to meet you, and thank you for being our invited speaker. And I'm sure that we will enjoy with your presentation. You can start your presentation.
Okay, thank you. Can I share my screen?
Sorry, I think Li Gang, please stop sharing you first.
I don't know how to turn off my screen. Let's see how to turn off. It's not often use the Zoom. Okay, maybe. Oh. I already stopped.
It's okay now. Okay.
Okay, thank you.
Okay.
Can you see my screen?
Yes, we see, and you can start.
Okay, thank you. Hello, everyone. My name is Jingxuan Zhang. I'm from Zhejiang University, and I'm a student of Professor Wang. Next, I will present our progress in optical super resolution and optics in curved space. Okay, firstly, let us review the concept of optical super resolution and some current research progress. We all know that a light beam can be considered as a superposition of many plane waves with different spatial frequency. This high frequency evanescent wave cannot propagate to imaging plane, which means that now the mode width is much narrower than the ideal situation. And after Fourier transformation to coordinate space, it cannot be an ideal imaging, cannot be a perfect imaging plot. It's not a delta function distribution, but it's a big spot like this. And on the other hand, when light propagates through a diffraction system, like a pinhole or slit, a diffraction point spot appears. According to the realist criterion, when two spots are close enough, we cannot distinguish them like this. This can be distinguishable. And this is just distinguishable. We cannot distinguish the 2 points. So this is so-called the diffraction limit that puzzled us for a long time in optics. And the early proposal and realization of super lens was to use material with a negative refractive index to recover and enhance the evanescent waves in near field. This is a current conception of the subwavelength imaging, and we can use the super lens to overcome the diffraction limit with like a severe super lens. And based on this, someone proposed a hyperlens that can transform all the evanescent waves into propagating waves. So this is the subwavelength imaging to overcome the diffraction limit. And nowadays, with the increasing development and wide application of laser technology, scientists have made significant progress in super-resolution fluorescence microscopy. For instance, the stimulated emission deflection fluorescent microscopy and this resolved and storm and palm technologies. And in our work, we changed the optical resolution in a new perspective by using the spatial curvature. To demonstrate our method, we need to firstly introduce the origin of our inspiration. In the past decades, optics in curved space have attracted much attention. The first side is the optical analog of gravitational effects. According to Einstein's theory of general relativity, gravity is a geometric effect of curved spacetime. Even light can be also distorted. So we usually use light to detect the gravitational effects in universe, like black holes, like dark matter or dark energy. But in practice, these experiments require a huge cost. And many scientists have proposed some equivalent systems which can simulate gravitational effects in lab, like BEC, and using fiber to simulate the effect of vertical horizon of light, and using the metamaterials to simulate celestial mechanics, and using the optical black holes to trap light and the observation of photon rings. The other side is to directly embed the curved surface into a three-dimensional space, like these surfaces of revolution. It allows light to propagate on such surface. This concept was firstly proposed by Betz in 2008. They theoretically calculated the propagation effects of light in the surface with a positive curvature and negative curvature. After 2 years, these effects were experimentally realized. Like we can see the propagation on a sphere and on a paraboloid. Later, many scientists studied more on the optical effects on various of surfaces. For instance, like this surface, they found the photon tunneling effect. And also the observation of accelerating wave packets in curved space and the spatial evolution in the HBT measurement, and also the self-interference near a Schwarzschild black hole. Inspired by these works, we reconsider a classical Fraunhofer diffraction problem in a curved space, and we see that the affection of spatial curvature on the optical resolution by calculating the size of diffraction spots. Okay. Firstly, we need to consider a simple model of surfaces of revolution with constant Gaussian curvature. It has metric forms like this. There are 4 types of these surfaces. With the blue surface represents that the Gaussian curvature is positive, and the red is negative. We assume that the light propagates along the longitude lines. It means the z direction. Light propagates along the z direction. And now we place a slit or 2 slits on the equator of the surface. Like we put the slits on the green line. It's an equator. And then we observe the intensity distribution after light is diffracted by a distance. In practice, we can write the wave equation of the electromagnetic field according to the metric. By solving this equation under Parexel approximation, we can obtain the point spread function. Then by integrating this point spread function, we can get the intensity distribution on the surface, like this formula. This formula is for the single slit case. And as a generalization, we also consider the double slit case. We can see that compared to the flat space, if we let this R, this R means the radius of Gaussian curvature. If we let R tends to be infinity, this formula tends to be becomes to a Fraunhofer distribution in flat space. Okay, the next we can see the diffraction intensity distribution on the surface. This figure shows the Fraunhofer diffraction distribution with different curvatures. The black dashed lines represent the distribution in a flat space. And compared to that, we can see that a curved space with positive curvature can narrow the diffraction peak and reduce the size of diffraction spot. This means that the two imagined points can be distinguished more clearly, which providing a new method to realizing the super resolution in optical imaging. And on the contrary, we can see that the negative curvature enlarges the diffraction spot and increases the diffraction effect, leads to a worse imaging. And this phenomenon is also applied to the double slit case. In addition, based on this figure, we also propose an Abbe limit formula. This is applied to the curved space. And this numerical aperture is a multiplication between the numerical aperture in flat space and the factor of curved space. And the above is our distribution of light propagation at a certain distance. We also show a continuous distribution in here. We can see more clearly that the positive curvature helps to focus light, and it reduces the diffraction effect, where the negative curvature is totally opposite. This is a propagation effect of light in curved space. We need to emphasize here that since the light is confined on a curved surface now, any distance we measured here should be a length of a geodesic on the surface. The geodesic reveals that the shortest path between 2 points in any matrix. So besides the intensity, we also need to calculate many geodesics, which is a complex process, and we don't talk here. In addition, we propose a method to flexibly control the optical resolution. Firstly, we define a quantity delta, which represents the relative difference between the beam width in curved space and in flat space. And this figure shows that the delta varies as the K is a Gaussian curvature, and this is the propagation distance. We can say in the red regions, it means the resolution gets worse, and in the blue region, the optical resolution gets better. So by this figure, we can control the optical resolution flexibly by only change the shape of curved surface. And moreover, according to the principle of transformation optics, we can equivalently transform a curved surface to a planar waveguide with a refractive index distribution. So then we can use the planar waveguide to realize the super resolution imaging. And this will be talked later. And next, until now, we have found that the influence of spatial curvature on the optical resolution and provide a method to control resolution. And next, we need to consider a fundamental question. The above conclusions are based on the assumption that light is propagating along the longitude lines on the surface. And we can only consider the case of constant Gaussian curvature. Okay, so what if the light propagates in another direction? Like it has an angle with the longitudinal lines. We still consider the constant Gaussian curvature firstly. Now the propagation direction, we can see that there is many angles. So we need to find another method to calculate the intensity, because the formula we obtained is above is invalid. Here we introduce an approach to solve this question. It is based on the Huygens principle, which is developed by Chen Yixu and can be used to calculate the light propagating in any direction and on any surface of revolution. Briefly, Huygens principle refers to that any point of the wavefront can be seen as a new point source, and they emit spherical waves and superimpose in the whole space. Here we assume that each wave propagates along a geodesic, and the final field distribution is a superposition of all the spherical waves, which is this formula. Therefore, in this process, we need to calculate many geodesics to calculate the geodesic length in this area. This area is also refers to the iconal of light. Although this is tedious, but it can effectively solve the problems with arbitrary propagation directions and arbitrary surface of revolution. And here we consider 3 surfaces with constant Gaussian curvature and 3 propagation directions. The conclusion we found here is same as previous. The positive curvature focuses the beam, and where the negative curvature enhances the diffusion effect. Moreover, we find that they are all same in any directions. This indicates that when Gaussian curvature is constant, the space is like uniform, and light propagation shows a kind of isotropy. To verify this, we also consider the surface with variable Gaussian curvature. Like this, we consider more realistic Schwarzschild black holes and a black hole with a dark energy, and also a surface with a periodic structure. Now we can see the curvature is varying, and the distribution of light is also changed with the propagation direction. Specifically, near the Schwarzschild black hole, we can see the beam width is initially as the same as in flat space. We can see these curves. Because the curvature is small when it is away from the black hole's horizon. Then it increases rapidly when approaching in the event horizon, leading to a divergence of beam width. If we consider a cosmological constant, it becomes to a Schwarzschild de Sitter metric with 2 horizons. And now the beam initially propagates in the Sitter domain with a curvature is positive. And so the beam we can see is narrower than it in flat space. When it is in the Schwarzschild domain, it starts to expand rapidly. We can see the curves. And on the periodic surface, the beam width also oscillates periodically. These results provide a method to detect spatial temporal curvature using the diffraction effect of light. We may detect the existence of black holes and dark energy or the other phenomena through the change of optical resolution. Okay, finally, we plotted the variation of the relative quantity that when the angle changes continuously. It is similar to the previous results. In addition, As mentioned earlier, we can transform the surface into a plane with specific distribution of refractive index. For example, we can transform a sphere into a plane. These two systems share the same dynamics of light, and we can use the planar waveguide to realize all the results we obtain. Okay, in conclusion, we systematically study on how the spatial curvature affect the diffraction effect of light. We found that the space with positive or negative curvature tends to decrease or increase the diffraction spot, which leads to a better or worse resolution. We gave a new avenue to control optical resolution beyond the diffraction limit using spatial curvature. And then besides, the variation of resolution gives an approach to detect the non-uniform space in universe. And our results has been published in the Photonics Research Journal. Okay, thank you all.
Thank you very much. Thank you, Professor Zhang. It was very nice presentation. And
Thank you.
actually, it was a very interdisciplinary seminar. Thank you. If there is any question, we have time to mention, raise questions. Is there any question?
Hello. If you want to let me, I have a question.
Yeah.
Before you asking a question, I want to thank you for inspired presentation, Professor. I have a question about regarding the application of Huygens principle. Can this principle be adapted to system with a negative refractive index? If so, how does the principle account for the unique wave propagation characteristics in such materials? Thank you.
Thank you for your question.
Yeah, I'm sorry, I don't understand. Or could you repeat again?
I want to know this principle, the Huygens principle, can be adapted to system with a negative refractive index.
You mean the Huygens principle can be?
Yes. Yeah. Can be applied to negative refractive index systems.
You
in
mean
such
the
material.
Huygens principle can be used in the negative refractive index, like this?
Like this. Did you simulate something about that, or?
No, we don't simulate we don't consider the structure with negative refractive index. We only consider the surface directly. We only consider the light propagates on the curved surface, not the material with a refractive index.
Okay, thanks. Thank you.
Okay, thank you.
Okay. And other question?